Got it. All right. Well, it's really great to be here. Thank you so much to the organizers for inviting me. It's really just such a spectacular location, and I'm really excited to learn, so much more about information. I thought I knew a lot already, but it's clear that I'll be learning a lot this week. Also, thank you to everybody that's presented this morning for setting up, computational mechanics for me, because, my perspective is largely as a thermodynamicist, as a physicist, and what I'm going to try to do for you is argue that computational mechanics, machine learning, that these have sort of roots in physics and thermodynamics, that there's a motivation behind it. Sorry, I think it just stopped. There we go. Yeah. So this talk is kind of at the intersection of computational mechanics, which is the field that I learned in my PhD under Professor Jim Crutchfield, and thermodynamics, which is perhaps the topic that has stuck with me for the longest, very rooted in information and entropy, and then machine learning, which everybody is interested in these days. And as someone who's interested in emergent intelligence, artificial intelligence is of primary concern. And there's a lot of overlap between these already. Thermodynamics has a lot of overlap with machine learning, just in terms of the sort of processes that get implemented. Stochastic gradient descent is essentially a thermodynamic process. It's essentially annealing. Computational mechanics is at its core about, well, not maybe Alex would argue this, but at its core about inference. It's about understanding data and processes and what's going on under the hood, very much like machine learning. But they each have their own sort of regime of expertise. I'm really focusing at the intersection of all of these ideas. And just to link it all together, it's all about entropy and information. This is the language that's really shared between all these disciplines. And at the core of all of these is a probability. And I'm going to use notation identical to Alex's, pretty much, where we have random variables, which describe the distribution. And then we have realizations of that come from that distribution, sunny, rainy, on any particular day, 1 or 0, X is realized from these up or down, if we're talking about spins. Now, in physics, entropy was introduced a long time ago by Gibbs. We get our standard P log P here with the factor Boltzmann's constant out in front. And instead of using a natural, or instead of using log base 2, we have a natural log. Whereas Shannon entropy, you forget the KB term and you take log base 2, because this is describing the average number of bits necessary to communicate. So you have that log 2 factor coming in. And you can show, or it has been shown that, with efficient coding, the average number of bits that you need to encode some signal, say coming from a distribution of like 80-20 over up and down, it has to be at least the Shannon entropy over those bits. And this is the same picture that Alex showed, which is, probability of one of these outcomes on the bottom, and how the Shannon entropy rate depends on these two. Physically, the meaning of entropy or information is not necessarily framed in a communication perspective. It's usually addressing sort of the properties of physical systems. It's often related to energy. For instance, if you have some thermal reservoir at temperature T, and you have some heat flowing into it, the entropy of that reservoir is directly related to the amount of energy that it's gained. So the heat that's flowing into it. And there's this proportionality constant T. So T basically describes the natural energy scale of that thermal environment, the energy scale of thermal fluctuations there. Now, just as a practical point for the rest of this talk, I'm actually going to switch to expressing Shannon entropy in terms of nats instead of bits, just so that the proportionality constant doesn't carry around this factor of log 2 forever. It's just a little notational convenience. So why is entropy such an interesting quantity from a physical perspective? Well, it's basically it's a sort of organizational, or it dictates a principle of organization. So in physics, one of the things you might be familiar with is the first law of thermodynamics, which says that energy is always conserved. However your dynamics behave, energy is preserved. But the second law of thermodynamics says that in an isolated system, entropy is always increasing. So if you were to have sort of a glass here, and we see that it's in the midst of shattering, how would we expect this system to evolve? Well, there are very many ways of that glass to fracture into many, many pieces and spread out over the kitchen floor. By contrast, there are very, very few ways for all those shards to reassemble into the configuration of, a coherent object that you can then drink from. So because entropy is increasing, we would generally expect this system to evolve towards sort of a shattered, disordered state, towards a state of greater entropy. And viewing this on a cosmological scale, the progression of the universe from a very hot, dense state to a very distributed state is, and sort of in line with is dictated by the second law of thermodynamics. You have, a very dense system spreading out into a much more dispersed system. And eventually this law predicts that basically we'll have heat death, that, all structure that we see and appreciate in the universe will be spread out into a, low wavelength photon gas as black holes absorb everything and then re-radiate it as Hawking radiation. It's sort of depressing, perhaps. This is the sort of informational principle of organization that we see in the universe. And yet, this is sort of the thing that motivates my research. In our corner of the universe, this is not the dominant trend that we observe over the last 4 billion years. We see as time progresses, we start with simple biomolecules that over hundreds of millions of years, self-organize into single cellular living organisms that harvest available free energy in their environment, that then self-organize into organisms, multicellular organisms with central nervous systems that are able to react to complex environments like the albatross flying over the wind field over the surface of the ocean, never actually flapping its wings, just making subtle adjustments. Then to collections of multicellular organisms, superorganisms like humanity, which is a global organism. And so we see this increasing complexity and intelligence. And is it possible that there are thermodynamic principles of organization beyond the second law of thermodynamics that govern non-equilibrium systems, that tell us how these systems evolve? And Jeremy England has done some basic explorations in these sorts of systems with driven spin glasses, trying to identify how these non-equilibrium systems evolve. But these are primarily computational, not theoretical explorations. My way of addressing this is to first address the idea of complexity. If we're going to talk about this progression, first we need to know what we mean by complexity, and then talk about thermodynamics, and then about learning. So to start off with, I will basically review what Alex talked about, which is we have a pattern, which is a process, a sequence of random variables, and the probability which determines the probability of realizing some sequence of elements. And then we can consider the entropy or the information of such a process. And again, using information diagrams, where we have this element representing the information in the past. And then we can look at something like the entropy rate. Alex talked about, the entropy rate as being this wedge, which is the information in the present that's independent of the past. You can also look at it as sort of the limiting average entropy per symbol if you divide by the number of symbols. And then Alex also mentioned the excess entropy, which is the information shared between past and future, which turns out to be a lower bound on the statistical complexity. And or basically any model that can generate the process is lower bounded by this excess entropy, which is why people relate it to complexity. But here the statistical complexity is, basically the entropy of the smallest function of the past, such that the information between that function and the future is equal to the information between past and future. And this is a minimum sufficient statistic of the past about the future, going back to the idea of sufficient statistics. So this is, you can draw this picture for all sorts of things. It doesn't have to be past and future. It could be, you could draw this picture from future to past as well and have retrodictive complexity as well. And that's where you come across causal asymmetries. You could do it for multivariate systems as well. And I just want to emphasize that these are probably the two most important quantities in computational mechanics. There's the entropy rate of the process and there's a statistical complexity, and these often get conflated and confused. People will think that, because a process is very unpredictable, it has a lot of complexity, but for the case of like a random coin that's maximally unpredictable, the thing is they're conceptually very similar concepts, because the statistical complexity is not the unpredictability, it's the difficulty of predicting it. So how much information do you need to carry in order to optimally predict your process? So that's computational mechanics. What does this have to do with thermodynamics and intelligence? Well, thermodynamics and intelligence has a very long history. Over 150 years now with Maxwell's demon. So James Clerk Maxwell proposed that an intelligent demon, by observing its environment, could precisely control and without doing any work, this door between two sides of a box of gas, and it could let particles go from one side to the other when they're moving quickly, but not otherwise. And in doing so, reduce the entropy and spontaneously transform disordered heat energy into ordered work energy. And that would seem to violate the second law of thermodynamics, turning disordered energy into ordered work energy, creating order out of nothing. But fortunately, well, maybe unfortunately, because actually, let's take a moment to think about the consequences. If this were possible, a lot of us care about conservation, right? We care about global warming. What's the problem in global warming? Well, we need energy, so we burn fossil fuels. Fossil fuels make the planet hotter. So we've got too much heat and we need more energy. Well, what if we could just do this? We're like, let's take all that thermal energy in our environment and just transform it into useful electrical energy. Let's just charge our phone batteries, our computers, our electric cars on the thermal energy in our environment. Unfortunately, that violates the laws of thermodynamics. That would be a type 2 perpetual motion machine, where you're using thermal energy as to do useful work. type 1 perpetual motion machine is where you create energy out of nothing. Type 2 is where you violate the second law of thermodynamics. So going to Landauer's bound, by the way, if you get the chance, try to copy this link into your browser and play around with this a little bit. I'm going to show you this in a minute. But Landauer realized that information processing itself, the operation of the demon's mind, has to counteract the benefit that it gains from its intelligence. And Landauer realized that, if you're producing some work and or if you're trying to, if this is work production and you have to erase a bit, that ultimately it's going to come at a cost. That's at least KT, which is the thermal energy scale of the environment, times log 2. And so here we get to sort of the concrete simulation. Can you see this? Yeah. So this is a simulation of a very simple 2-bit memory. Okay. Oh no. Well, unfortunately, I can't access the Zoom controls right now. Oh, really? Oh, here we go. If I hit escape. All right. Zoom. So what this is an energy landscape, because we're doing physics right now. This is a potential energy landscape with an ensemble of particles representing a bunch of different realizations of the system, essentially representing a distribution where you have metastable potential energy wells, one storing, it's storing a bit. You've got a 1 and a 0. And it's important that these are metastable, because if you're storing a 1, you want to be sure that you're storing a 1 later on. Now, what erasing a bit would be doing is that it would be resetting the memory to a default state, say 0. And this is what, say, the daemon has to do. Say the daemon looks at its environment and it measures something about it and takes some action based on that measurement. So it started in the 0 default state, and then based on what it saw, it's now in some distribution. So if you grab this center thing, you can move the energy landscape, and this is how you control a thermodynamic system, is by changing the energies, but it comes at an energy cost. And that's being accounted for at the bottom here. On average, this is how much energy that you have to expend on each particle. And basically, we see that as we raise the energy of these particles, you're investing energy. So here I'm just lowering the barrier so that the particles can transition from one side to another. And then I'm going to tilt to one side to get them all on the 0 side. This is a protocol I'm implementing that's inspired by John Beckhofer. If you look up his papers, he does this optimally with feedback potentials.
This is very cool.
Oh, good. I'm glad you think so. Oh no, one particle got over, so it's not a perfect erasure. But now pretty much everything's in 0. And even though I've reset the energy landscape to the original distribution, I have incurred some average energy cost. This, on the right side, the energy scale is KT. So this is 2 KT. And this is in agreement with Landauer's bound, which this is greater than KT log 2. So no matter how slowly I did this, how cleverly I did this, I would always incur an energy cost that's above about this much right here. And so that's sort of a way that you characterize the relationship between information and energy. Sorry, I'm just going back to the presentation here. All right, so that's Landauer's bound. And if you want to generalize Landauer's bound, the way that you would see it, say, is, you have some process now where you have some informational degrees of freedom and a hard drive that you can write to. And so you have some energy flow from the heat bath to the work reservoir or vice versa. And then you have some information flow. So there's information in the heat and it's being split up. There's information and energy in the heat. And it's being split into information that goes into the information reservoir and work that goes into the work reservoir. And according to the second law of thermodynamics, if you're considering this as a closed system, the entropy is entirely the information contained in this hard drive and that contained in the thermal reservoir. And so we have the entropy of the reservoir plus the entropy of the hard drive has to be greater than or equal to 0. Well, by energy conservation, this work has to be equal to minus the amount of heat, which has to be less than or equal to T times the change in entropy of the hard drive, or KBT times the Shannon entropy. So this is Gibbs, this is the Shannon. So that's basically the generalized Landauer bound. That's sort of the argument that information, energy, these are inextricably tied to one another. And so you can very quickly see that if you think about how is this machine manipulating this hard drive. Let's say we think about this thing called an information ratchet. You can also call this an information transducer, where the hard drive is represented by a string of bits, and you have a bunch of inputs, which you have the daemon operating on one at a time and outputting into outputs. You can show that the rate of work production is upper bounded by KT, the thermal energy scale of your environment, times the entropy rate of the output minus the entropy rate of the input. And this is one of our results from a while back. So, yeah.
Can you, at that point, maybe go back to the question that Jim asked before? Would the thermal reservoir be maximally or minimally informative? Like he was asking, is random noise now containing maximum information or 0? Because that's also striking me.
Yeah. So as a resource, maximum information or maximum Shannon entropy is the worst thermodynamic resource. So the higher that this is, the less energy can be extracted. So it's a less functional informational fuel. Does that sort of, I mean, when I think about information, I'd say I think about it more along the lines of Alex's perspective, which is, really conceptually information, when we think of, oh, we have information about a system, that's really mutual information. That's a reflection of some correlation that we have with a system. If that system is totally predictable, if there's 0 entropy in it, we can't have any mutual information with it. We can't have any predictive capacity for it, or there's no point in having it. So going to, the work production as it depends. Sorry, I realize I need to close this again. All right. So going back to how this hard drive functions as an information fuel, you really need to know what's on it. And this is where we start to go in the direction of inference. We need to figure out sort of the patterns that exist in our information reservoir. And, this work production is going to be dependent on the initial Shannon entropy and the final Shannon entropy. So what are the different sorts of things we have? We have the maximally entropic signal, which is white noise, where you have no ability to produce work. There's no value to that as a thermodynamic fuel. Or you could have a completely predictable sequence. You could have the all 0 sequence. And for that, the initial entropy is 0, which means you can produce work up to KT log 2 per symbol that you look at. And then you have something like the complete works of Harry Potter, which is in fact a deterministic process. There's only one configuration for this entire sequence. And so you should be able to produce a lot of work in the process of harvesting energy from it. However, if you were to look at any individual like subsequence, it would look nearly random to you. And so that's a reflection of the fact that Harry Potter itself, or any say data file that you take in general, once you break it into binary, even if it's deterministic, is going to appear like random noise. And that reflects the fact that it's complex. It requires memory of what you've seen in the past in order to make the best possible prediction of what's coming in the future. So now we have a sense of like what the different sort of informational resources are. And we want to know how can we figure out what's on the tape? How can we infer what's on the hard drive thermodynamically? So our challenge is doing thermodynamic learning through maximum work production. We want to harvest maximum work from our data by saying that we have a bunch of different agents that each interact with the data that's coming from our source. And each of them tries to produce some amount of work from it. And we take the one that produces the most work and say, this is our maximum work agent. And the way that these daemons operate, these are information engines, is that they have some agent memory that operates locally on some interaction bit yi at the time I. And this is very much like a stochastic Turing machine, where you have some read-write head with some memory that goes between different elements of your system. Now, because these operations are happening locally, you know that the heat that gets dumped into the thermal reservoir only depends on the Shannon entropy of your local variables, the memory of the daemon and the interaction bit. And that allows you to sort of decompose the entropy rate into pieces. So, our heat is lower bounded by this change in Shannon entropy, but the global change in entropy of the system includes both the heat and the entropy of the whole system. So, all the bits, including the memory altogether, have some change in Shannon entropy that contributes to the entropy of the system. And then the heat also has this Shannon entropy of just this local subsystem. So we have a difference in entropies between the local subsystem and the entire system. And it turns out that this entropy production is lower bounded by minus the change in the mutual information between the memory and the interaction bit in the remaining bit stream. So any information that you lose between this system and the remaining systems that are unchanged corresponds to dissipation that's unrecoverable. It corresponds to irreversibility. It corresponds to wasted energy. And this is what we call the modularity dissipation. So, just being totally concrete about this, we have, our random variables, our local system and the remainder of our bits, and we do some operation to it, and this overlap is in general going to reduce. Our goal is to basically preserve the size of that overlap. So if you're harvesting energy from patterns, what you wind up doing is you have some random output. You want to harvest all available free energy. So you have basically white noise as your output, and the input is structured. And due to that, we can sort of reduce this modularity dissipation to a term that's only dependent on the inputs and the memory and how the memory updates. And then we can ask, of the many ways of erasing information, because there are many, you can just shake up a box and that will effectively randomize it. You can let it thermalize, but you're not necessarily going to harvest any work in the process of doing that. So of the many ways of erasing this information, which is best? Well, we have a random variable x here, we have flexibility in, but not so much flexibility. One thing we know is that it's non-anticipatory. Because our system is causal, it doesn't have any information about the future beyond what can be predicted from the past. On top of that, the thermodynamically best model must contain all information between past and future. And this is something we can prove by minimizing the modularity dissipation. So this implies that the minimum entropy production implies that the hidden state X, the memory of the daemon, is predictive. Or in other words, it implies that the memory of the daemon must be a sufficient statistic of the past about the future. So we see that we arrive at these sort of informational principles by insisting on minimum entropy production, by insisting that we maximize the use of our thermodynamic resources. And so just returning to the epsilon machine, because the epsilon machine is this minimal sufficient statistic of the past about our future. We have the statistical complexity, and we have causal states, which are functions of the past, say A, B, and C. And then we have a start state, and we have symbol labeled transitions. So given that we know we're in some state, and given the output, we know what our next state is. And this is basically our topology of the machine. And then on top of that, we have transition probabilities. And this sort of specifies our full set of model parameters. We have, our hidden state alphabet, our input alphabet, start state, topology, and probabilities. And this is important because this is the class of agents that we're inferring over. And we can exactly calculate the word probabilities from these features. And so what the requirement that we produce zero entropy implies is basically our architecture must reflect the epsilon machine. So first of all, the entropy of the agent's memory must exceed the statistical complexity. This is the principle of requisite complexity, that in order to harvest all available information in your environment, you must at least be able to store the predictive complexity of your environment. So there's like this requisite matching. This is an extension of James's rule of, Ashby's rule of requisite variety. And this also tells us that there's basically a way of designing, based on your epsilon machine, the agent that harvests maximum work. In essence, you use the topology that updates the causal state to update the state of the memory as well. Yeah.
So you mentioned so far there's a thermodynamic cost to modularity.
Yeah.
And I think in the paper you also mentioned a benefit of building modular models.
Right.
So what would be the benefits of modularity?
Right. So I would say, just practically speaking, let's say if you, going back to this picture of a daemon here, how are you going to control this system such that you are able to harvest all energy, not just over this local region, but over the whole bit stream? If you want to access all correlations, you have to design an energy landscape that includes all variables and it is just very high dimensional and has a lot of nonlinear couplings, a lot of features that may not be practically implementable in your physical device. Does that make sense?
Yeah, because I try to keep translating this to how can it help us to build our macroscopic modular models, and where would we find the optimal trade-off between building subunits and building instead on the other machine learning model that takes all the data in at the same time. So can this help to inform this question?
I think there's definitely going to be, for different processes, a length at which it may be advantageous to just extend the window that you're viewing and controlling at any given moment. Say if all the correlations are contained within series of length 2, it might be worthwhile to forget about the memory entirely and just operate on series of length 2. But the reality of a lot of these processes, non-Markovian processes, is they have correlations that are infinite length. If you take a hidden Markov model, it's generally going to have time correlations that can't be captured in just a few time steps. Does that sort of make sense? So we have sort of a prescription for how to build our machines, and on top of that, we have a prescription for how to manipulate energy landscapes, given that we have a particular input or output distribution. Say that we expect 80% up, 20% down. How do we efficiently transform this? Well, you need to initially change your energy landscape to be in equilibrium so that there isn't probability flow in the system. And then you quasi-statically evolve to your final distribution, and then you quench to that distribution. And in doing so, you find that your efficient engine is able to extract energy not just on an average basis, but on a per realization basis. And this is where we need to go, because machine learning doesn't happen on average, it happens for particular input sequences. You have to do inference on a particular input sequence. So with that, we have, computational mechanics gave us this equivalence between a process and its estimated epsilon machine. It's minimal predictive model. Now we also have an equivalence to the efficient agent that harvests all accessible energy from it. And with that, we now see that the work production itself for a particular input sequence, if we have a model theta, an epsilon machine model theta, is linearly related to the log likelihood of the model given the data that is put into the machine. So there's this extra term here that corresponds to the benefit of randomizing each of the bits. But what this tells us is that the maximizing log likelihood is the same as maximizing work production, which means that MLE is the same as maximum work production as a strategy for learning from data, at least when you're dealing with epsilon machines. So just to draw this parallel between learning and physical systems, in machine learning, we have data. In thermodynamics, we have physical systems that store that same data. Then you have a model in machine learning for your data. And then in thermodynamics, you have an agent, a daemon, a controller that manipulates your physical system and has a model of the underlying data that it uses to determine how it manipulates that system. And then in terms of measuring the performance of the model, you have something like the log likelihood. And the best performance measure, or the most common performance measure in thermodynamics, is work production, which, as it turns out, matches the log likelihood. So these are two sort of equivalent frameworks, MLE and maximum work production. So what happens if we actually maximize work production? Well, this is the basic idea. We have a bunch of candidate agents with their internal models, and then we have some data of length L, and then we plug that data into each one, and we take the agent that maximizes the work production. And say we do this for some memory size n, and we maximize over all n state models. So that's what we're determining here, is the model that maximizes the work production. And we can also evaluate the work associated with that. Just for our purposes, I'm about to show you some plots where there's actually something in the black box. It's a 5-state model determined by theta prime. That's a 5-state epsilon machine. It has some entropy rate, which determines sort of a theoretical limit on how much work could be extracted from this system on average. This is the information processing second law. We've got, log 2 minus the entropy rate of that model. And because of requisite complexity, we know that we need 5 causal states, or we need 5 memory states in order to harvest all available information from these 5 causal states. So let's start with one-state models. Every one-state model looks in the following way. You've got a single memory state, and you've got some probability b of seeing 0 and some probability 1 minus b of seeing 1. And you have the inverse temperature beta, and you will maximize for a particular topology by doing this decomposition into elements or edge weights here with the topology plugged in. And you find that you can break this into an expression that uses only the number of times the causal state S receives input Y. So you just have to do this counting problem. And that tells you that the maximum edge weight that you plug in for your epsilon machine is basically the fraction of times the causal state S receives input Y. For a particular topology, this is the way that you find the maximum work machine. And so doing this for one-state machines, we plug in some length L word, and we consider the maximum work agent as we increase the length from 0 to 100. And so this is the maximum possible work that could be extracted on average asymptotically. But transiently, the machine thinks that it can harvest much more. But then as you feed in more data, it approaches a value that seems to be much less than the actual asymptotic work rate. And this makes some sense. This indicates that there are temporal correlations in the underlying data. Then if you were to, say, use two-state models, you see a longer regime where it thinks you can harvest more energy than is actually available in the system. But then it sort of equalizes as you increase the training length to a value that's slightly higher than if you only allow yourself one memory state. And then if you give yourself 3-state models, again, you see the same sort of trend, a longer regime where you think you're harvesting more energy than is actually physically possible. And then you approach some asymptotic-ish limit where you're harvesting more than either example before. So in general, we see that there's this advantage to allowing yourself more memory. You strictly give yourself an advantage by having more memory when you're maximizing work from some energy resource. This is kind of like the principle of requisite complexity, but there's some nuance to it. But we really want to know, this doesn't actually tell us how well any of these engines learned. So for that, we need to do validation data. So we take new information from our black box and we plug it into our system, and we see, with our maximum work agent, how well did it do? Using our MLE model, how well did it do? And we can evaluate that by looking at the average work production for every sequence from our model and averaging over the probability of realizing that sequence from our black box. And then we can consider sort of the asymptotic work rate. And we see this picture of, there's this rate at which information is flowing from our actual black box model into our guessed model, and a rate at which energy is being produced. And we can compare. So here's the training work rate for all these different processes, the average amount of work over, when we train. But when we look at the validation work rate, we see that when we think that we're extracting a lot of work, we're actually overfitting. We're doing thermodynamic overfitting. Down here, this is actually divergent work, divergently negative work production. So the machine breaks basically in this machine. it thinks it knows precisely what's going to happen, and then it sees something that it doesn't expect, and that breaks the machine. But as you train on longer word lengths, it sort of approaches, this IID estimation of the model. Same thing happens for length 2, but in this case, as you increase the memory of the model, we see that this regime of overfitting extends for a longer period of time. But on top of that, we also see that there are these different regimes where you start to learn more and more about the process as you train on longer word lengths, where until by length 100, you're extracting much more energy on average than the single state models. And then you see the same for the length 3 or the 3-state words, where you have a very long regime of overfitting, and then you actually do very good prediction of your model after that. So this is very effective learning for this particular process. But just seeing these all together, we see that memory offers a universal benefit in training, but often leads to divergent dissipation and validation. So the benefit of memory can only really be found for large training sets. As machine learning experts, this is probably obvious. Just to make the point, though, these plots really depend on what sort of training word you're looking at. We see in this case, for this training word, we actually never fit to any decent model when we have length 3. So how do we address this problem? Well, in machine learning, there's some strategies for doing this. And there's this result we have for correlation-powered information engines that hints at a solution or a partial solution. So if you have, say a period 2 input, you might design a ratchet that has 2 memory states to try to harvest energy from it. But the problem with it is it's going to have 2 non-ergodic solutions depending on where the process starts. One where the energy is produced, and one where energy is dissipated. Now you need to synchronize to the work-producing region, and to do that, you have to incur a cost. You add a synchronization state, but the result is that there's this trade-off between synchronization, the cost of synchronization, and the asymptotic work rate. And so going towards machine learning, if you have some machine learning task like learning an input to output mapping, where you have some matrix W that determines this, you want to say, minimize the distance between, the target and your estimate. But the problem is, if you don't constrain this matrix, you can wind up with some solutions that don't generalize very well. So you add a cost to the weight matrix that regularizes, that sort of makes the more extreme solutions less beneficial. So what you actually try to, what you actually find the minimum argument for is this, distance term plus this, you have some term lambda times the average weights of the matrix. Can we do the same thing in thermodynamics, where we have some thermodynamic benefit from the word, but also some cost of synchronization that corresponds to a regularizer that allows it to generalize? So we have a similar strategy where we basically incur the cost of synchronization by insisting that we cannot start in a particular start state. Instead, we insist that we start on a uniform start state. And if we do this, we see very different results. So here's sort of the problematic case where you don't learn anything for 3-state memories. But if you add this synchronization feature, the dashed lines show you how the training results, you see that you extract less work through training, but you see that you almost entirely avoid this divergent dissipation regime early on you have it, but as you train on longer word lengths, you are able to sort of synchronize to the process. And sort of, you don't wind up overfitting to patterns within the data, because you need your system to sort of discover the pattern from every start causal state. So this sort of overall indicates that, you know, a number of different things, that maximizing work production leads to learning complex models from patterns. This is something that we can see sort of computationally, but we also see that overfitting leads to divergent dissipation, which is basically entropy production, and it's more common for complex information engines. But we also see that there's both a thermodynamic cost and benefit to complexity. So if you have, you know, a complex environment here, and your agent is more complex, there's a force to be less complex. But also, if your agent isn't able to capture the correlations, there's force to be more complex, to sort of converge and have this force towards complexity from both, the appropriate complexity from both directions. And we see that learning can be partially regularized by requiring that agents autonomously synchronize to their environment. So in terms of, like, I know this is all from a physical perspective, but I think these strategies for learning can potentially be extended beyond the thermodynamic regime. And I hope that we can have some conversations going forward on how these might be applied. So with that, I'd like to thank my collaborators on this project and funding sources. Yeah.
Thanks, Alex. So we're going to take questions for Alex. Sort of breaking, we're doing about half an hour lunch. We'll just sort of merge into the panel discussion. The math questions, so we can also go into a more broad discussion at the same time. But let's start with the questions for Alex.
Well, thank you for the talk. It's more a remark than a question. I see how we get to a common understanding of the term information and work very hard towards it. It's just with a remark just coming from ecology and biology, that the use of the term evolution or evolving as you use it in physics, it's almost the opposite what we mean in biology, because we're talking about unique events or unique history of events. And I think we have some problem if you want to bridge these various disciplines around the table with the physical evolution.
Well, when I say time, when I say evolution, I'm usually talking about time evolution, which just means pushing your index t, yes, in a positive direction. And that differs from a biological or evolutionary perspective, because evolution is, I'm not quite clear on the distinction there.
Well, we don't have an equation for it, but I just want to remind you of this metaphoric transport and the metaphoric spillover, because it's not physics. So at least we can show that. We cannot show that it's physics. So.
Anytime we get people from multiple disciplines, language always becomes issue. So thank you for raising Peter and then Andreas.
I actually have two questions. Right.
Sure.
Question number one. So thank you very much for the talk and really know about this here. I actually have a question which I've often wondered about, which pertains to happened right in the beginning of the talk.
Yep.
So I come from originally from mathematics, and then there is when you talk about the second law. Also, Landauer was bound, and actually did this nice simulation you showed. To me, it's always been a bit mysterious. Actually, can you put on the glass?
The glass? Yeah. Yeah.
So to me, it has always been a mysterious. Is the second law an axiom or is it a theorem? Where the difference would be presented as an axiom, right? So like, this is just how it is.
Yep.
But when you were talking about this, you seem to present it as a theorem. You said like we have actually some rules for dynamics,
Mhm.
and because there are many ways in which this can happen, and not many ways in which this can happen, it follows that. And so I always wonder, like, does it follow from something else, or is it like the basis?
Yeah, great question. This is something that bothered me for a long time as I was studying thermodynamics. The rule that entropy is increasing is often presented, especially in undergraduate physics, as if it's just a law without ever being proved. And fortunately, in recent years, maybe the last 3 decades, we now have an understanding of where the second law comes from. And it's basically a result of assuming a unique sort of start state, assuming causality, basically. So, if you're trying to prove that information or entropy is increasing in the universe, the way that you actually define the entropy of the universe is the entropy of what you can see plus the entropy of what you can't, right? Your environment, what you can't control, it's like your heat bath and all that. And basically what you have to assume in order to guarantee that entropy is increasing are 2 things. You have to assume that the heat bath is initially uncorrelated with you. And you have to assume that the heat bath is initially in equilibrium. If you don't assume these things, you can actually see cases where entropy reduces. So this is, I hesitate to make too strong a claim about this, but honestly, this is, I think, a very deep philosophical problem in that assuming that we start in this state with every experiment is maybe functional and reproduces all of our experimental results. Causality as an assumption is a very useful assumption, but we don't actually have a proof for why that should be the case.
So that would be your axiom.
Yeah, well, that would be my starting point personally, is that there's sort of this, if you made the opposite assumption that at the end of your experiment, your reservoir is uncoupled with you and in equilibrium, then you would infer actually that minus the exact same amount of entropy would be produced. So I can actually, if you want at a later date, or later time, we can talk about where the proof of the second law comes from. But yeah, it's a challenging one.
That clarifies a lot. I mean, that somehow seems. I mean, I understand exactly what you're saying.
Yeah.
Yeah, thanks a lot. This was interesting. There's a lot of physics that was way above my head. But I think what is really nice is how you link some physical properties with machine learning, which is, of course, interesting. But itself, what I was wondering, where do you see, can we learn more about physics by taking experience from machine learning in this way, or rather the opposite way? Do you see there a way that we could, 2 domains could learn from each other?
Certainly. The problem is I know a lot more about physics than I do about machine learning. So, but I think there's just a lot of work being done in machine learning. For instance, in trying to, a lot of machine learning, as I understand it, is about finding minima, in sort of like an energy landscape, and there are ways of sort of, doing, it's basically optimization, right? And there are these strategies for doing that may correspond to physical processes that we haven't considered yet. That's one possibility. I would say actually this idea for regularization that I came up with, this was in some ways inspired by machine learning. This idea that, okay, we need to do something to this physical process that ensures that it doesn't dissipate infinite energy. That it did come from learning a little bit about machine learning. So that's a little bit of the reverse there. So I'd like to learn more.
Yeah, cool. Thanks.
Yeah.
So take this just to, so I'll let you ask your question, but after that, we're gonna skip over into plenum and I'll sort of start a discussion around that. So if you have any other questions, just hold them.
Yeah. So my question is the following. I mean, I think earlier we mentioned that
it's important to understand that information is physical, and then I think what you've done is try to link that to, even though to some extent, this picture is quite revealing, in the sense that this is for an isolated system, and the entropy is increasing. When we deal with most of our systems, they are not isolated, they're open systems. And that is when you get the properties of emergence, the kind of thing that you're showing. And so I'm trying to see how you go from an open system concept to, isolated system concept to open system concept, and then you could apply it to the observations and things like that, or is this whole idea of epsilon machine restricted to our thinking about essentially an isolated system and not an open system? Because, I mean, if that's the case, then all data that we're seeing, irrespective of periodicity, is anchored on a very fundamental assumption of an isolated system.
I would say like equilibrium thermodynamics as it was originally conceived like 150 years ago, very dependent on this idea of, yeah, that's much more focused on these isolated system perspectives. And my way of, and still to a degree, when I think about thermodynamics, I mean, quantum open systems is a huge field now, or quantum thermodynamics. But my personal preference is usually to think in those cases, how can we close the system? What pieces can we add such that the system is now closed? Like what reservoirs, like what non-equilibrium sources. But maybe there is some work that takes the perspective that these open systems, these non-equilibrium systems have a mathematical language, thermodynamic language, all of themselves, that focuses not on energies, but on surprisals. And so I would refer you to Paul Riker's and Michael Simon's work on this stuff. Personally, where you don't talk about heats and works so much as excess heats, excess works, housekeeping heats, housekeeping works, which are a different sort of breakdown, but allow you to talk about dynamics. I feel like I'm going on a little bit.
That up. I actually want to.
Okay. Sure.
Well, I'm going to ask you to drive to a slide real quick.
Okay, I'll do that.
Because for being actually sort of bridged where I was going to go with this. And I also asked Layla to possibly help with this. So if you're okay for me to take this right now, just because it jumps right off. Okay. So could you go to like one of your slides where you have the evolution with the word length?
Oh yeah, sure.
So I'm going to continue to make the theorists uncomfortable in here.
This is what you're looking for?
Yeah, this is perfect. And also build on Praveen's point and sort of like, how can we think about bringing it back out to the domain sciences where we know that a lot of these assumptions don't hold, out there when we're measuring things at macroscopic scales. And so also heading back to the point of evolution, I mean, sort of what this seems to me is one point of possible development would be you have some agent that sort of learns to harvest this energy in a way that's useful for itself, given some time history, and that sort of converges around something. But then we have, the non-stationarity of things happening, which would lead to sort of evolutionary trajectories of like these machines sort of modifying themselves in time.
Yeah.
So you would, you have an optimal thing for a stable system, but as you disrupt it, you start to like, oh, this node goes away, or this, the weight transitions start to change, and this would be very discrete, but in this framework, but potentially offer a way to sort of capture that adaptability of these systems. Do the theorists in here have thoughts on whether or not that would be a viable sort of strategy to simulate?
I mean, from a thermodynamic perspective, this is one of the things I'm most interested in is, how, what's happening here is we have sort of this external algorithm that's searching for maximum work production. But to me, it sounds like, what you want is sort of more to autonomous dynamics that naturally discover intelligent processes or naturally learn themselves. And that's what I'm hoping to find is like, are there physical processes that naturally lead to maximizing work production, that naturally lead to entropy minimization, that naturally lead to learning, right? And stochastic gradient descent again is like one of these thermodynamic processes that overlaps with machine learning, and so I have some intuition that maybe that's a place to look.
And we do see things like that in landscape evolution to non-perfect degrees, but
So you're talking about an adaptive learning process.
I mean, learning as an overloaded word, but yeah.
So maybe as a reaction to your reply, I think this is gradient descent is an especially interesting one. Because this is like in the machine learning world, this is kind of a deep mystery that in many cases it does not overfit. Whereas it should be overfitting like crazy. You train a 1 billion parameter network on much less than 1 billion bits of data. If you just use other methods, there are many local minima in your landscape. So there's many ways of maximizing likelihood. That's exactly what it does. Most of them give you extremely bad predictions, and you get the thing you have there on the left, you get it forever. But gradient descent, and then of course it's always a bit like dark art because there's some parameters you have to set it, you have to set them right. But it usually doesn't do this. And so there is something inherent about those dynamics. And there have been actually very nice papers where they actually, so they often don't regularize when they train these neural networks. It seems crazy from a classical statistical point of view. So there are some very nice papers about that where they look at what gradient descent does on simple problems, where you can see that actually there are several local minima. And it finds very special local minima, which minimize some kind of special norm. So basically, yes, I think there's a lot to be discovered. There may be also, if you look at these dynamics from a physics perspective, there can be enormous differences in the different algorithms people use. And stochastic gradient descent, they might have hit on a very good one, more or less by accident.
Well, by accident or inspired by, so much of physics and like Ising models and all that. I mean,
I would say it's also like very much like the first thing you would think of.
Yeah.
And then they invented backpropagation, which was actually not inspired by physics. And then suddenly they could use it. So I'm maybe you're I think in too high regard. I think it was mostly like, okay, we just have to minimize this. Let's put in some statistics. But
yeah.
Okay, maybe I'm a bit too cynical there.
I would like to follow up on the question that Andreas made before, where he said, how can machine learning learn from physics and vice versa? And I was wondering, do you think it's most efficient by learning from each other on, making analogies on a high level and say, well, this kind of concept could be transferred to the other domain, or to actually go to the physics of computation on the computer and say, try and evaluate or try to optimize machine learning approaches by looking at the actual thermodynamics of the computation and realizing some physical optimization there, or do you think that's too far fetched?
Oh, I think people are starting to do that. I think there's this normal computing company that's looking at how to sort of reframe a bunch of computer science problems as thermodynamic problems. There was a paper that came out, thermodynamic linear algebra or something. I don't know. I mean, I can't comment on how successful it will be, but I'll say I think the processes are inspiring. I mean, so we've got like quantum computing, right, which is a mechanism or using physical dynamics to solve problems that are hard when you limit yourself to digital processes, right? Discrete digital processes. And I think we can apply the same sort of ideas to thermodynamics, where, you know, there are processes that are more naturally represented in sort of this thermodynamic landscape, right? And that's kind of what D-Wave is too, right? It's kind of like an, you know, people say it's a quantum computer, but it's also like it's an annealing machine. It's finding local minimum. You know what I'm, D-Wave? Oh, D-Wave is one of the earliest commercial quantum computers. So, yeah. So sorry, did that?
Not exclude that approach, basically.
I wouldn't exclude anything. No. I think it's too early to do that. But I'm the theorist, so I don't really know what's practical.
So Ocean, maybe we can take your comment and then possibly open it up for like if people want to change topics or switch gears or something. But,
Just extending on what you said, Peter, it occurs to me that in the large machine learning models, you randomize your weights before you start the gradient descent, and then you have a randomization process in the gradient. You're actually imposing a very strong regularization right from the beginning, a different kind, so that you know, there's a way in which that's regularization that helps you avoid it.
Well, the randomization is certainly crucial, but I don't think it's enough to explain. So, there must be a lot more going on because there are also other ways, right, which also where you would also put in a random input, and you get a very bad local minimum in your service. So that there are somehow several things work together there. So you would think it's kind of food for thermodynamics.
Yeah, but I was looking at that example where how it should, where he started with a uniform distribution of states. And by randomizing on the weights, you're doing something like that. You're starting with a uniform distribution of weights because each weight doesn't have a specific meaning. It's giving a chance to learn what it wants to be. Anyway, that was just
To add something maybe, there are groups actually which try to use like this principle to that learning dynamics. So basically try to analyze the learning dynamics, and they usually express it in like Bourgeois dynamics or stuff like this, or use thermodynamic principles to get what could be behind. I'm not sure how practical this is or useful, but there are groups. Just to say it's not like some people are doing this.
Oh, yeah,
cool. Does anyone else have a new topic or a jumping off point? Go for it.
Can you go to your supplemental slide real quick, the one that had that reservoir computer?
I didn't mean to show that, but okay.
Going back to the topic of the white noise, like does it have the maximum information or the minimum information? If you put that linear layer on the end of that, could your reservoir just simply be like white noise, although systematic, getting there in a systematic way? And that linear operator at the end of it does the operation which Hosha mentions that giving it context. So like if like some system is just like pure white noise, but you know what, you could train like a linear operator on the end of that to get a context with what it's supposed to have information about, what that information is supposed to be about. Does that make any sense? That's what
I think so. I mean, when I was considering showing this slide, but I didn't ultimately, like the parallel that I was drawing was like, you know, these reservoirs, you know, they're specified by some hidden dynamics, and then you have some layer, right, that tells you, or sorry, there's some layer that sort of gives you sort of a lens onto what portion of the dynamics you care about, right? And you have the same sort of feature here where you have hidden dynamics driven by your system, and then you have a layer on top, which are the probabilities. And so, yeah, I think this linear layer that you're using is ultimately like honing in on the feature of the dynamics that is most relevant.
I guess that's like my favorite paper of the last like 3 or 4 years.
Oh, really?
Yeah.
Cool.
I guess like the idea that the arbitrary dynamics can be mapped linearly onto your target variables,
Yeah.
like no matter what they are, is just really intriguing, and the white noise comment kind of made me think about that.
Well, that's what I've been wondering about too, is like what sort of hidden dynamics can you sort of, there's sort of like an epsilon, maybe there's a general type of epsilon topology underneath where you can just infer almost anything you want, and then it's just fitting the probabilities on top. That's the question. So
So I haven't read this particular paper, but that sounds somewhat familiar to a lot of these like newer state space models that are becoming very performant. So, as a point of reference, if you want to check out.
So yeah, a few things. One, it's just a technical question, but I was wondering how you determine your lambda in your
the lambda in the
parameter weight or penalty.
yeah, it's basically determined by the dynamics themselves. So there's just going to be a cost of synchronizing from, you know, 2 different states that will turn into an average. I've considered other sorts of synchronization parameters, and there are choices for which it's basically Bayesian on each state. So I just like that parameter, where it's you get Laplace's rule of succession based on the counts that you get. But
Okay.
yeah.
So secondly, going back to what Peter said, I was thinking maybe with gradient descent, the choice of so you use the gradient and the Hessian, right, to determine the step length. In that way, you maintain a structure among the parameters in the update, whereas other methods may find a similar local minima, but they don't preserve that structure between the parameters, and that structure may be important when you go in prediction. So that would be my explanation. And the other thing is, I was wondering, because you asked, so to explore the relationship between feature information, but that's related really once you have a model and you want to determine parameters, and Shannon information. Because now we go back to that whole debate with Keep on Clue, because essentially what he does, he just reduces the information of the data. You relax that. If you lower the information content of the data, then you don't constrain as much and you maintain larger uncertainties. And the question is, I believe there's a fundamental underpinning there that relates to feature information, but also to Shannon information. But then you should be able, yeah, it's a longer story, but that's something I've been thinking about. So I don't know if anyone's ideas about that.
There, not to be a thermodynamicist, but there are Fisher information pops up in thermodynamics as well, as so there's the Fisher information matrix. And Gavin Crooks and I think David Sedak and a few others have looked at sort of how to optimally control a system, and it turns out that there's sort of a geometric way of doing this, and the metric itself turns out to be, I believe, the Fisher information matrix.
The problem that we always dealing with is that the models that we have significant structural errors. And the data that we use is subject to a lot of uncertainty. And then a lot of the theoretical, assumptions that are made, they can go out of the window. That they're just not realistic. And anyway, thank you. Great presentation.
John, I was trying to understand the back and forth in the question. But if I want to say something, tell me if this is standard. But in a generative model, generative machine learning model, essentially, if I understand correctly, that part of what is, when you pass it to a generative model, you get cats, dogs. So, that's what I thought you were talking about. Am I correct? Because you've learned basically some mapping or transformation, which goes from pure random noise to some structured system, right?
Yeah, but I guess not pure random noise, something that will look like random noise after it's been through a systematic dynamic process.
So it has structure in it, but you just can't detect it using your normal tests of randomness.
Right, because you have to learn the weights on that linear layer at the end. And so those weights have to know that if those weights we'll learn from those hidden dynamics. We'll learn, yeah, from the hidden dynamics, how to get that mapping.
So you're saying the hidden weights are discovering the pattern in the seemingly random noise, or
The final linear weights at the end. So with that paper, I think my interpretation of it, I've never actually talked to anyone else who's interested in reading it. I'd like to talk to you about it, I think.
right?
But it basically says that the dynamics are not important.
I think the dynamics are very important.
Well, it says what the dynamics are not important. The dynamics have to be sufficient.
Oh.
Then at the end of a sufficient dynamical process, you can have a linear mapping to any target you want.
Right. So it's like if you have sort of this universal brain or something that's being driven by, signals, you can always zoom in on the piece of it, which is reflecting the dynamics of the system that you want with this linear layer.
Yeah, why I think that's super interesting is because what Jasper said is that we're dealing with models that have structural uncertainty, but what it really is they're not really representing the system we think that they're representing. But then if you throw it in as a layer on the machine learning model, then you can find a mapping to your target, no matter what the target is.
Generally, so we actually chatted with everyone at XFI about this thinking, and I think we agree the dynamics are very important because they need to be in this specific regime of high dimensional. Jim McGill has said this: the edge of chaos is what people talk about. Like it has to be both. Yeah, I know. It has to be both expansion, like it's able to expand out into dimension, but not just fill space, right? So the dynamics have to be at that particular regime, but then the argument is that they don't need to, other than that, be specifically tuned to what system you're trying to model.
Yeah, I really regret saying that.
No. I know what you mean, but that's I think what you were getting at, right? It's like you don't have to. That's right. Fit the structure of the states, underlying states, to whatever the system is. You only have to train once it's in this regime. You don't have to train on the options. Right.
So also we're basically out of time, so I think we should. There will be more. Yes, yeah, there will be plenty of time to continue.
Thank you so much.
Also, I wanted to try